What we got to in the lecture last week is that we spent a fair bit of time going through how the DCF basic access works. And if we remember, a station must do the diffs and the medium must be idle for that period. Then it does a back off, a random back off. It must be idle for that period. If so, it transmits its data. The receiver waits a short interframe space and sends back an ACK. If someone interrupts you, you must defer until they've finished transmitting and then try again. What causes collisions? What are some ways that a collision can occur in the basic access? How can we get a collision in basic access? A collision is when two transmitters transmit data frames at the same time. How does that occur? If they're on the same channel, but with the basic access mechanism, if someone else is transmitting, you should defer. What causes two to transmit? What are some conditions that would cause two stations to transmit at the same time? Well, we saw one case. If we see if we draw a partial of the sequence of transmissions from two different stations, then if someone else is transmitting, then a station will defer until they stop transmitting, until the ACK is transmitted. And in fact, maybe one station was transmitting and another two stations had to defer. Another two stations wanted to transmit data, but they had to defer, and they defer until that final ACK. Let's say the final ACK was here. They defer effectively up until that ACK is finished. Defer means we wait until the medium becomes idle. So if these two stations had data to send, but they detected someone else transmitting, maybe there's some other stations, then they would both defer until that final ACK is transmitted, and then they would finish that deferral and restart that procedure of waiting for diffs, back off, and transmit. And we saw one case if two stations choose the same back-off interval, then in theory they would collide, because they'd both finish the deferral at the same time. They both start the diffs. The diffs is the same period, 50 microseconds. If they both choose a random number which is the same, two different computers choose the same random number, then they'll back off the same number of intervals. Say they both choose 3. Medium is idle, it's idle, it's idle. Both of them finish the back off at the same time, therefore both transmit the data. There's a collision. So one condition that causes a collision if two stations come out of deferral at the same time and choose the same back-off interval. The back-off interval is based upon choosing a random number between some range, like say between 0 and 31. You've got 32 possible values to choose. What's the chance of choosing the same back-off interval there? What's the probability that two stations choose the same random number? You need to return to your high school or basic statistics. 1 over 32. So it depends upon the range that we have. If we were choosing between, let's say between 0 and 3, That is, we could select 0, 1, 2 or 3. If there is 2 stations, then A then we have 16 possible combinations. A could choose 0, 1, 2 or 3. B could choose, because they choose them independently, B could choose if they chose 0, or B can also choose 0, 1, 2 or 3. So they are the 16 possible combinations if we can choose from 0 to 3, just from 4 numbers. Which ones cause a collision? How many of those would cause a collision? A collision would occur if 2 stations choose the same back-off period, the same number. This would. If A and B choose the same number, if A and B choose the same number here, here, 2 and 2, or 3 and 3. 4 out of 16 cases would cause a collision. That is, there's 4 out of 16 cases where they choose the same back-off period. That's if you choose between out of 4. If you choose out of 32, we have 1 out of 32 chance of getting a collision there. And that's why we double this effectively, this maximum number. If this becomes 63, then the probability of collision is 1 over 63 between 2 stations. By doubling this maximum value of the contention window, CW max, then the second number in our random interval, then we double the chance, or we halve the chance of a collision occurring due to the same back-off. So one condition that leads to a collision is when the 2 stations choose the same back-off interval. That's unlikely. It won't happen very often. What else could lead to a collision? Well, we mentioned briefly one case is called what's called the hidden terminals or hidden station problem. If we have our access point and we have 2 clients, A and B, A and the access point are within range of each other. So whenever A transmits, the access point hears that. It's within range. And same in the other direction. B and the access point are within range of each other. Whenever the access point transmits, B will hear it. And A will hear the access point as well. But A and B are outside of the range of each other. They're too far away. So if A transmits, the access point hears that transmission, client B does not. We can think the signal is so weak that from client B's perspective it's just noise. It's too small. So A and B are hidden from each other. They're hidden stations or hidden terminals. The result is that if that situation arises, when A starts its diffs and back off, it checks, no one else is transmitting, finishes its back off, starts to transmit the data. B does the same. B wants to send some data. Diffs, no one's transmitting from B's perspective. It cannot hear anyone else transmitting. During the back off, even though A is transmitting data, from B's perspective it cannot hear that. It cannot sense that transmission, so it doesn't think anyone else is transmitting, completes the back off, and B starts transmitting the data. So we get a collision at the access point because we now have 2 transmissions at the same time at the access point which receives both of them, and we get all data lost at the access point. So these hidden stations can cause collisions even when we have different back-off intervals. So that's a problem. What's the probability of this happening? If we have hidden stations, what impacts upon the chance of this happening? We saw with the same back off, the probability depends upon this random interval. The higher this value, the lower the probability of a collision. What does the probability of collision depend upon in this case, in the hidden stations case? What increases the chance of a collision here? Data size. The larger the data, the higher the chance of a collision. A collision is when two stations transmit data that overlap in time. They don't have to be transmitted at the same time. A transmitted here, B slightly later. But if they overlap in time, we've assumed that if two transmit data overlapping in time, from the receiver's perspective, that's a collision. If the data is small, and let's say A transmits here, assuming that stations have data ready to transmit at random intervals, it comes from the application, the chance that another station wants to transmit that overlaps with this compared to a large data frame, here's a small data frame, here's a large data frame, the chance that B wants to transmit that causes an overlap with A is smaller with a small data frame than with a large data frame. B needs to start transmission between here and here. That is, if B starts the transmission here, it will overlap with A, just by a small part. If B started the transmission here, it would overlap with A. If B started the transmission here, it would overlap. So in fact, the probability that two stations transmit such that they cause a collision depends upon the length of that frame. With a longer frame, the probability that they overlap increases. Because if we ignore these, if B starts transmitting way back here, if it has a long frame, then we can have an overlap and a collision. So the larger the frame, the larger the chance a collision will occur. How big is a data frame? Well, there's a maximum size. Wireless LAN supports 2,312 bytes. Normal wired LANs only support 1,500. So normally the maximum size is 1,500. Normally we'd like the data frames to be as large as possible, most applications, because then there's less header relative to the data. The larger the data frame, the more efficient we are. But the larger the data frame, the larger the chance of a collision if we have hidden stations. There's a trade-off there. So how do we fix that? That's the problem. This is trying to show that if we have data with a large data frame, there's a high chance of collision. If instead of transmitting the data frame, we transmit a small frame first, a small RTS, request to send frame. If we send small frames first, then there's a less chance of collision, and follow up this RTS frame with a clear to send acknowledgement frame to inform the other stations that transmission's about to take place. So with the alternative to basic access mode is called RTS-CTS mode. RTS, request to send, CTS, clear to send, where we have two different frames. In addition to the data frame and the ACK frame, we have an RTS and a CTS frame. the sender of the data, the one who wants to send the data, initially sends an RTS to the destination saying, I request the opportunity to send. If the receiver is prepared to receive the data, they'll respond with a clear to send, saying you're clear to send the data. And then they'll send the data frame. And then we'll get the ACK. So we have these two additional frames, RTS and CTS, size in the tens of bytes. And we also use data and ACK. Let's go through this diagram to illustrate the process. The diffs and back off, the ACK and data is all the same as before. There's nothing different there. The only difference is that we have this request to send and clear to send frames first. So in this example we have A, the access point, B and C. In the scenario, every client, A, B and C, is within range of the access point, but out of range of each other. A can hear the access point, but A cannot hear B or C. That's our assumption here. So A has some data to send, it waits the diffs, the back off. Instead of sending data frame now, it sends this small RTS frame to the access point. When the access point receives it, we have the short interframe space, and then it responds with a clear to send if it's ready to receive the data. So diffs, back off, RTS, short interframe space, CTS. And when A receives the clear to send, it's clear to send the data. It waits a short interframe space, transmits the data, access point receives the data, short interframe space, sends back an ACK. So everything's the same as before, except we've got these two new frames in here. The time between frames is always the short interframe space. Another new thing we have here is both the RTS and CTS frame in the header include some indication of how long A wants to transmit for, the duration that it needs to transmit the data. So when the access point receives the request to send, the access point knows how long the data transmission is going to take from A. Let's give it a number. Without doing all the calculations, let's say we have diffs, back off, RTS, CTS, data, ACK. From A's perspective, when it sends the request to send, in the header it includes the duration field. And that is a value that indicates how long it expects to complete this transmission. A knows that this should be the short interframe space. So the duration to complete the transmission is, after the RTS, we have one short interframe space plus the clear to send plus another short interframe space plus the time to transmit the data. Because A knows the data size it wants to send, it can calculate the time to transmit the data transmission time, plus a short interframe space, plus the time to transmit the ACK. Again, the ACK is normally a fixed size, so we can estimate how long that will take to transmit. So the concept is that in this RTS frame, A sets the value of duration such that it tells anyone who receives the RTS how long this is going to take, from RTS onwards to the end. So it sets the value. When, sorry, this is not B, this is the access point. when the access point receives this frame and everything's okay, it's ready to receive some data, it responds with a clear to send. And in the clear to send frame, there's also a duration field. And it's simply the updated value based upon what this was. The clear to send, the duration is how long it takes to complete this transmission, which is this minus the clear to send time and the short interframe space. So the access point now sends a clear to send frame, including the duration to complete that transmission. Then data and then ACK. Now look from the other node's perspective, B and C. B and C do not receive the RTS. A transmits a request to send to the access point. If I'm A and the access point is here, we're within range, but B and C are out the back, then my transmission will not reach B or C. So neither B nor C received the request to send. They don't know it was transmitted. So they just keep going about waiting for their chance to transmit. The access point receives the request to send, it's within range, updates the duration to complete, and responds with a clear to send. Both B and C are within range of the access point. If they want to communicate with the access point, they need to be within range of it. So both B and C will hear the clear to send. The clear to send is sent from access point A, but B and C receive that as well. And when B and C receive a clear to send, and it's sent to someone else, it was sent to A, they recognise, okay, someone else is about to transmit. Someone has responded with a clear to send, not to B, not to C. Therefore, it must mean someone's about to send some data. And for how long are they going to send the data? It's specified in the duration field in the header. So B and C now know that someone else is about to transmit data nearby. And they know the duration from the header field. So they automatically defer for that duration. They don't check whether the medium's idle or not. They don't care. They just listen to the clear to send, and they know the duration that someone else is going to transmit, and they automatically defer for that time. Don't try to transmit. The name of this duration, or the time that they defer, is called the network allocation vector, the NAV, N-A-V. But the concept is defer without waiting to check whether the medium is idle or busy. So B and C defer until the transmission's complete. And when they finish their deferral, they can start their steps of diffs, back off, using the same rules. Once the back off's complete, send the RTS. C doesn't hear the RTS. It's out of range of B. The access point hears the RTS, responds with a clear to send. C hears that clear to send. So does A. C hears the clear to send, defers automatically. B gets to transmit the data, and then C continues back off, RTS, CTS, data, ACK. So what we've done with the RTS, CTS is that we first transmit a small frame, the RTS. We've said before, the larger the frame, the larger the chance of collision. By sending smaller frames, we reduce the chance of collisions there. If two stations want to transmit an RTS at the same time, very small chance of collision. And more importantly, we have an RTS-CTS mechanism such that stations outside of the range of the transmitter of the RTS are likely to be within range of the access point that sends the CTS, which tells B and C that someone else is about to transmit, and they will defer automatically according to the duration in the frame. This is a way to prevent this many collisions due to hidden terminals. And that's it for RTS CTS, or the basics at least. So in your exam in 2 weeks, you need to be able to draw these types of diagrams, do calculations of how long things take, and work out, is there going to be a collision or not? So if you look in past exams, you'll see sometimes I'll set a scenario where there will be a collision, and you need to work that out. Or work out what's the total time to transmit. So given some other information, you can calculate the transmission times and so on. Yep.
This is work with other ESs that use the same channel.
Yes, anyone who receives the CTS should defer.
CTS from
Oh, RTS or CTS. RTS or CTS. Yep. Yeah.
Not only our level.
No, because normally if you sense the medium and the medium is busy, it doesn't matter who's using it. If it's someone else's access point, I don't care. If it's busy, I need to defer. So the same concept's here. If I receive an RTS, it doesn't matter who sent it. Someone has sent it, someone is about to send, because they're requesting the chance to send, I need to defer. So if you hear an RTS and it's not to you, you must automatically defer according to the duration in the header. And same if you hear a CTS and it's not to you, you need to defer according to the duration. So that stops collisions between different networks. Yeah?
But is there any chance of collision in this scenario? Like if this period starts at the same time and we have the same amount of back-off period,
So is there a chance of collision? That's the question. Anyone have an answer? Yes or no? There's still a chance of collision. Let's show briefly what that scenario leads to a collision and see how that impacts on performance. A access point, we'll just consider B, no need for C. A has some data to send, B has some data to send. They do their diffs. Remember, A and B are outside of range of each other. They can't hear each other. They choose a back off, whatever value it is. And it turns out A's back off will finish here. B's back off will finish here. They cannot hear what anyone else is doing, so A sends the RTS to the access point. B also, at the same time or overlapping in time, sends an RTS to the access point. There's a collision at the access point. Two people are transmitting frames, A and B, to the access point. The access point cannot understand either of them. So there's a collision there. In the same way that without RTS CTS, the data frames can collide. This is the same scenario that leads to two data frames colliding due to hidden terminals. But the probability is much smaller because an RTS frame is usually 10 to 20 bytes. It's a small frame. A data frame is usually hundreds, 1,000, 1,500 bytes. It's a large frame. The probability of collision of two small frames is much less than the probability of collision of two large frames. So that's the benefit of using the small frame here. Still a chance of a collision, but very small. Yes?
What if any text might have that duration to transfer?
Okay, so this duration field is important because it tells others how long they need to defer. Can A calculate what the duration will be? Well, the back-off is already complete. When we transmit the RTS, we need to know how long it takes to get to here. Well, it should be RTS, CIFS. CIFS is fixed. The duration to transmit the RTS is fixed. It depends upon the data rate, which A knows, and the size of the RTS, which it also knows. CIFS is fixed. It knows that once access point receives the RTS, it's going to wait for that fixed period of time, so it can predict what that will be. Size of the CTS is fixed or known, so it can predict the time here. CIFS is known. A knows the size of the data. It already knows the frame it's going to transmit. So it should know that and the time to transmit. It knows the data rate. And same here. And it should know the size of the ACK as well. So it can predict quite accurately how long it will take. What could go wrong? I'm not sure if it could make an incorrect prediction there. It should be able to predict what those exact values are, set the duration. If there's a collision for some other reason, some other station has caused a collision, then what that will mean is that these two stations will defer, but they will still defer less than what they need to do. So that would be okay. So I don't think it can go wrong there.
But we have not considered the propagation delay here.
Okay. I have omitted the propagation delay. How long is the propagation delay? In fact, in the standard, there's some assumption about what the propagation delay will be less than. It will not be greater than some value. So it can make some prediction there. In the original standard, there was an assumption that the distance was less than 300 metres. I think it was 300 metres or 250, but say 300 metres. Therefore, we can calculate the propagation delay, just 300 metres divided by the speed of light. And we find that that's a very small value. We could incorporate that in here, that is the propagation delay. If it's 300 metres, then the propagation delay is 300 metres divided by 300 million metres per second, which is 1 microsecond. The CIFS and DIFs are in the order of tens of microseconds. So if the propagation delay was not 1 microsecond but 1.1, it would make very little difference. So yes, there is a propagation delay, but it's very small compared to the other parts, and you could make the duration slightly longer just to take into account the propagation delay. So RTS, CTS, same rules as basic access, except after the back-off, don't send data. First, request the opportunity to send with an RTS, and then once you're clear to send by receiving a CTS, then send the data. If the access point receives a request to send, but it knows that, let's say we had a scenario, how can it arise here? If, I can't see the scenario in this diagram, but if it happened that the access point receives a request to send, and the access point knows someone else is about to send, then the access point doesn't have to respond with a clear to send. So if the access point knows someone else is transmitting, it will not send the clear to send. That is, it will not tell A it's clear to send because it's not clear to send. Someone else is going to transmit. So that's possible as well. Any other questions on the basics of RTS, CTS? Any questions? No? Okay. So, with long data frames, it we've got a larger chance of collision due to hidden terminals. If we have hidden terminals, we won't always have them. It only arises when the arrangement of nodes is that the two clients are outside of range of each other. But it can happen. A longer data frame increases the chance of collision. Therefore, by using this RTS, short RTS at the start, we decrease significantly the chance of collision here. And using the CTS, we can inform other nodes. And they will automatically defer. So when do you use RTS CTS and when do you use basic access? Well, RTS CTS is good when we have hidden terminals. Basic access is good because it doesn't have this extra overhead of these RTS CTS frames. This introduces overhead where we're not sending data. It reduces the throughput. So there's a trade-off there. And in the standard and in the devices that you're using, there's the RTS threshold. It's the number of bytes above which, if a data frame is above that threshold, your device will use RTS CTS. Let's explain that. The concept is that with small data frames, basic access should be okay. Not so many collisions, even if there are hidden terminals. Because the chance of collision rises as the data frame gets larger. So with small data frames, use the basic access mode. With large data frames, if you use basic access, there's a larger chance of collision. Therefore, if you have hidden terminals, it makes sense to use RTS CTS. So there's a parameter which is called the RTS CTS, or simply the RTS threshold. So when I want to transmit a frame, I know the size that I want to transmit. I compare it to the threshold. If the size of the frame is larger than the threshold, use RTS CTS for that frame. If it's less than, use basic access. One of them's less than, one's equal to, I don't know which. I think if it's greater than or equal to RTS threshold, use RTS CTS. Less than, use basic access. So on every individual frame that you transmit, the frame size is known before you transmit it. It's compared to the threshold, and that determines which mode to use. And when you look at the parameters for your wireless access point, you should find that parameter somewhere. That's the comparison of basic access versus RTS CTS. So use the RTS threshold. That determines which mode to use. So I think it's not available via the web interface of your access points, this RTS threshold. You will see it on your clients. I think if you open up the configuration of your laptop, you'll find, if you look hard, RTS threshold. So you can change that value. It's got a default value. The higher the value of the threshold, let's say if the default was 512 bytes. If the value was 512 bytes, it means if you've got a frame less than this, basic access will be used, greater than RTS CTS. If you increase it, then that means you'll use basic access more often. That is, for all the frames less than 1024 bytes, use basic access. So you'll use basic access more often, which is good for performance so long as there are no hidden terminals. So if you know there are no hidden stations in your network, then a high threshold is good. But if you know there are If there are hidden stations, you want a lower threshold. If you know that there's not, use a higher threshold. It's not easy to determine what is the best value, because it depends upon the number of hidden stations, which it's hard to predict, because a station may move into the network and become hidden, so it's hard to know beforehand. It also depends upon other factors. What's the best value of the threshold? How much data stations are sending? How often they're sending? Using RTS, CTS may lead to other problems. It may stop stations from transmitting when they could in fact do it. We get what's called the exposed terminal problem. What you'll do for your homework, we care about the MAC performance. Your assignment's about the MAC performance, so we won't talk too much more in the lecture, but your assignment is about, for example, seeing how the RTS threshold impacts upon performance or throughput, seeing how different parameters impact upon your throughput, and you've got to measure the throughput with your access point. This explains some factors that impact upon performance. I think we'll leave that for now. You'll investigate that in your assignment. This one just lists the default values for our parameters. We've seen this last week, I think. The parameter values differ for the different physical layers. And when you do your assignment, you will take some measurements. You can validate whether they make sense by doing some simple calculations and seeing if they're roughly correct. Some simple calculations would include adding up the time it takes to do the diffs, the back off, RTS, CTS and so on. This time is the best, well, this time indicates how long it takes to transmit one frame. You can calculate the throughput for that one frame. It's from here to here is the total time, and you know the data size. So you can get approximate measures of performance on paper as opposed to just measurements. But you need to make some assumptions about what is the back off. You need to choose a random number. Well, you could have a minimum value, a maximum value, or possibly an average value. Here's an example of using an average value. And with 802.11g, with an average back off of 7.5 slots, then the time it takes to transmit using basic access is 334 microseconds, giving us a throughput of about 36 megabits per second. Data rate 54 megabits per second. Throughput in this simple calculation 36 megabits per second. But it doesn't consider collisions and other people transmitting and you deferring. So it will go, in practice, less than this. But this gives us some upper limit that you may achieve.